software called GRIN, Graph Theory Interface, to teach and learn graph theory as a ICT tool. So it is an ICT tool. So short in a while, I'll be sharing my screen to you all, presentations and this. Okay, and this software is easy to use. That's why I stick on to this. There are many other softwares that are available to study graph theory, but this is easy to use by both by students and teachers. So let me start my presentation. And at the outset, I thank the management of Rajalakshmi Engineering College, Professor Dr. Muthuswamy, for inviting me to address this gathering.
Thank you, sir.
After this session, I will be taking up questions. Okay, let me share my screen. Yeah, I am sharing my screen now. Hope it is
It's
visible.
visible, sir. Yes, sir.
Okay. So this is Professor Venugopal, Controller of Examinations of Sri Chandrasekharendra Saraswati Vishwamaha Vidyalaya, sponsored and run by Sri Kanchikamma Utpitam Charitable Trust. I am here since 1997. This is how you reach me. Okay, you can make a note of it. You can reach me on my WhatsApp for further doubts or clarifications. You can reach me on my mobile. So this is what we are supposed to do now. Basic graph theory with GRIN. GRIN is a graph theory interface, graph interface. I will use it as an ICT tool. And as such, I will be telling about the graph theory concepts also side by side. Graph theory concepts also side by side. I don't assume that the viewers know graph theory. Okay. This is my request to all. You clear up everything in your mind, be a clean slate to learn this concept. Have the mindset of a child. I understand you may be graph theory experts, you may be professors, you may be researchers in graph theory. Still understand that this session is on GRIN as an ICT tool to teach and learn graph theory. So this disclaimer, first one, though this is a free limited version of GRIN, is still available on web. I will give you the link. I'm not sure whether the updates are available from the creator. The original page by the creator is not updated. And earlier he used to sell it for 500 vertices, advanced version. Now only the limited version is available. Even that is for 50 vertices, that is good enough to teach and learn graph theory. The images are taken from various sources, and I will be creating images using the software GRIN. Definitions are taken from Wikipedia for ease. Thank you. So this graph interface is a powerful tool. It is easy to use. It is run by menu. I will be showing it shortly. And these are the links from where you can see about the software and download. Okay, and the last link gives about to some other software, Graph T, something which is similar to GRIN. I will not get into that now. Okay. So what will be covered in this talk from GRIN? I will tell you, I will demonstrate using the software GRIN and how to add the elements of the graph, how to build a graph with the vertices and the edges, how to change the size of the graph, how to move vertices, and to enter the edge weight and all that. Maybe it directed graph or undirected graph. We can copy the image to the clipboard and put it in your Word file or something. The basic metrics of the graphs, density and all that, Hamiltonian path, Hamiltonian cycle, Eulerian path, Eulerian cycle. And what about bridges and cut points, coloration, simple edge coloration, and automorphism, groups, minimal spanning tree, shortest path, k shortest path, salesman problem, maximal flow, and pass if time permits, critical path. I will not get into Petri nets, okay, because I assume the what is that? the participants know about graph theory. Petri nets is something else. We will not touch it now in 1 hour duration. So this is about the Green software, what it can do, taken from the website. Okay, it can do coloring, minimal spanning tree, shortest path, as I told you. And this is the screenshot of, I will get into that software directly now, but this is the screenshot. What it can do, it is illustrated here: minimal spanning tree, shortest path, maximum capacity path, maximal flow, and critical path is disabled now. It will come, it will be enabled when the graph is a project. When the graph is a project, critical path will be enabled. And if you treat it as a network, these are possible. If you treat it as a graph, you can find the quick metrics, you can do coloring, the paths and cycles can be dealt with, cut points and bridges to about the components, and the soft automorphism can be dealt with. I will not touch the simulation part, okay? I won't have time, but it can be done with ordinary Petri net simulation. And the SNA procedures also I will not touch, but it is possible. So let me introduce that software straight away first, then I will get back to this presentation. Okay. So this is the software interface. Okay, and you see that this goes up to 40 vertices or something. Okay, let me try whether I can maximize this. So this I will first start telling about how to build a graph with this Grin software. Okay. I told you this Grin software may not have updates, but still this software fascinates me for its simplicity. Okay, it is very useful. User interface is very simple. It can be used from right teaching and learning to up to some research also, because the most of the graphs we do in research are up to only 40 degree, I mean with 40 vertices, so it can be used in research also to some extent. Okay, this you see the white patch over here. If you click on it, a new net will open. Okay, this is the new net opening. You will see a number of buttons over here. Only one button is enabled now. See here, I am pointing my cursor. This is about add point. So if I click that, I will be adding points. So let me add points. Okay, I have added points now. Now you see further menus are enabled. Add a edge, remove a point. Okay, delete edge is not enabled as there are no nets. You can delete a component and you can rearrange them. Okay, increase X and Y sizes. If you so go to this menu, you can add a vertex, delete a vertex, move a point, then merge 2 points. All that is there. Let me tell you how to draw an edge. Okay, let me delete an edge. Delete point. I am going to delete this extra point. Okay, let me click on this add edge button and click at the source and click at the end point. Edge will be built. Okay, this I will repeat this. Click at 3, click at 4. So it is building. Click at 4, click at 2, click at 2, click at 5. Like that I am drawing. Okay, so let this be a graph. This is a graph. And these are called vertices. And these lines are called edges. Now I can put weights to the edges. What are the weights to the edges? Maybe it may be the distance from 1 to 2. Okay. If 1 and 2 are network points, this if you put the edge weight, that can be the broadband width or something. Let me put weights to this also. Let me go to see the menu over here. This is the network. Let me go to the table and add weights. Maybe I am adding weights. So some weights I am adding, random weights. Okay. Random weights I have added. Okay. Now let me see the network. Let me right click and say show edge weight. You see that I am including edge weight also over here. Okay, 6 edge weights are included. So you can build a graph, you can give edge weights. Now let us see what can be done with this graph, the minimal things. Okay, so a graph is a picture with the vertices and the lines joining them. The lines can have weights. Maybe if it is 6, it may be the distance from 1 to 2. It is very useful to have weights. You can have directed graph also. I will come to that later. Now, with this graph, what can we do? What can we start doing? It is very easy. I am telling you, folks. Go to this property, treat it as a graph. Treat it as a graph. Get quick metrics. What are the quick metrics? Let me click on it. Let me see over here. The quick metrics, the connected component is 1, radius is 1, diameter is 2, graph is not regular, degrees of the points is listed here, and degrees are sorted. Now, what are these basic, these metrics? Okay, so let me go back to my presentation. I will tell you something about the basic graph theory terminology. Don't worry, I won't get deep into the definition. Definitions are put just for the sake of completion. For those who see this presentation, they can understand what do this menu do. So these are examples of some graphs. Graph theory is an entity. Graph is an entity with vertices and edges, I told you. These are the examples of graph, Hewitt graph, Peterson graph. Those who are familiar with the graph theory may know about this. Astrologers graph, your horoscope can be treated as a graph. This court maze, okay, this can be treated as a graph. I am telling you where are the graphs getting into our life. So graphs are with the points and lines. Where do these graphs occur in computer science? It occurs in programs, data structures, computer networks, circuit layouts, and all that. And the flow chart can be also thought of as a graph. The organization chart can be thought as a graph. It is a downward tree. Let me get into how graph theory came into existence. So it is about 3 famous problems: the Königsberg 7 bridges problem, Chinese postman problem, and the New York street sweeper problem. I will not dwell into this much but this is a problem of traversing the 7 bridges of a old city called Königsberg, with the traversing each bridge only once. So this started the history of graph theory. And the Chinese postman problem is about the visiting and about the postman visiting every part at least once. And this sweeper's problem is same as this Chinese postman problem, where it is a directed graph. Okay, so such things gave rise to the theory of graph theory, concept of graph theory. So this is the basic terminology. Graph theory has vertices and edges. Okay, you have undirected graph, directed graph. Directed graph, we use arrows. Okay, adjacency, when U and V are connected by E, I say U is adjacent to V and E is incident with U and V. You have other terminology. Order of the graph is number of vertices. Size of the graph is number of edges. Degree of a vertex is the number of vertices adjacent to V, that is the number of edges that are incident at V. A graph is regular if all the vertices have same degree, then it is regular. Complete graph, it has all possible combinations of vertices in edges. Isomorphic graphs are graphs which are drawn in different space but essentially same. For example, Peterson graph have a number of isomorphic variants. Each of them you cannot even find out whether it's a Peterson graph, but various variants are available. Length of a graph is the number of edges contained in the graph. The radius of a graph is the minimum of all maximum distances between a vertex to other vertices, and the diameter is the maximum distance between any pair of vertices. Distance is the number of edges in that. If you consider 2 vertices, the number of edges between the 2 vertices is the distance between these 2. Okay. graph, I am going to show all this. That is why I am getting into this. The graph density is the ratio of number of edges, the number of possible edges. That means the graph is more dense when it has more edges. If it has maximum edges, it is dense. If it has no edges, it is sparse. Less edges or more no edges, it is sparse. Eccentricity is the maximum distance between a vertex to all other vertices is the eccentricity. Let me come to this later. I will get back to the software. Now let me see what are the metrics that we saw now. Metrics, you see that the radius is 1, diameter is 2. See that diameter is 2 because the maximum distance, the maximum length 2 to 3 and 3 to 4 is a length. So diameter is 2 over there. So let me get into further density. Let us see density. I told you about density. Density is more when the number of edges is more. A complete graph has the fullest density. So what is the density about this graph? See, there are certain edges missing. From 1 to 5 an edge is missing, 5 to 4 an edge is missing, 1 to 3 edges missing. Okay, if all vertices are connected to all edges, that is a complete graph. But what about the density of this graph? Let us see. So density is 3. Density is 3, and the greatest clique is 2, 3, 4. What's a clique? The clique is an undirected graph. It's a subset of vertices that every two distinct vertices are adjacent. A clique is the subset of a graph. Whenever you take two vertices in that, they will be adjacent. They will be adjacent. The maximal clique is a clique in the truest sense. It cannot be extended. Okay. Independent set is the set of vertices, no two of which are adjacent. A clique is a set of vertices. Any two of the vertices are adjacent. A anti-clique is a set of vertices, no two of which are adjacent. I will illustrate over there. Okay. Let me get back to the software. See, it says greatest clique is 2, 3, 4. Density is 3. Let us get back to that. 2, 3, 4. You see that it is highlighted with red. It is the maximal set where, see, 2, 3, 4 are available. 2 is adjacent to 3, 4. 3 is adjacent to 2, 4. 4 is adjacent to 2, 3. Okay. So if you consider these two vertices, 1 and 5, you see that they are not adjacent to each other. This is a anti-clique. This is a anti-clique. Okay. So let me see further. So these are the independent set. You see, greatest independent set is 1, 3, 5. What is that independent set? Let us see. 1, 3, 5. You see that this 1 is not adjacent to 3 and 5. 3 is not adjacent to 1 and 5. 5 is not adjacent to 1 and 3. They are highlighted with red. So this is anti-clique. This set is an independent set. So let me go for further analysis. Did I tell about point cover? I will come to that. Vertex cover or point cover is the set of vertices that includes at least one endpoint of every edge of the graph. You follow this? There are many edges of the graph. They have two endpoints, and this vertex cover should have all vertices, that includes at least one endpoint of every edge of the graph. So this is in one sense the vertex cover or point cover. Let us see the point cover. What is the point cover? Point cover of this graph. Point cover. See, point covering number is 2, and the smallest point cover is 2, 4. We will see here 2 and 4. You see that 2 has this is 1 to 2 and is an edge, 2 is here. 5 to 2 is an edge, the vertex 2 is here. 3, 4 to 2 is an edge, vertex 2 is here. 3 to 4 an edge, vertex 2 is here. See, 4 connects this 2 and 3. So this 2, 4, two vertices have the end points of at least one end point of all the edges. So this is a point cover. Okay. So let me get into coloring. Okay, I will tell about coloring. I will go for some other graph. So I told you about point cover. Point cover is the set of vertices that includes at least one end point of every edge. It need not include both end points. It will happen when it is a self cycle. Okay. What about coloring? We do coloring in graph theory. Coloring is draw colors, put colors on the vertices so that no two adjacent vertices are of the same color. This coloring is useful in many contexts. For example, you can even frame the timetable of your college using the concept of coloring. What is the timetable? So suppose a student registers for more than one courses in this era of fully flexible credit system. Okay, suppose a student registers for graph theory, suppose he registers for discrete mathematics. So his timetable must be framed in such a way that the period of graph theory and the period of discrete mathematics should be on different slots. That means they should be differently colored. If they are of the same color, that means this fellow will have to go to the same place. So coloring is useful in many contexts. Now we can draw a graph and try to color the graph quickly. And the minimum number of colors required for vertex coloring is called the chromatic number. You might have heard about the 4 coloring problem. Any map can be colored with just 4 colors. That if you take India map, with 4 colors, you can color every state such that no two adjacent states have the same color. Okay. So let me try coloring of a graph. What do I do with the coloring of a graph? Let me go for some other graph. Okay. Let me close this and go for a new graph. Let me go for a graph. Okay. Let me try this. Let me draw edges. Okay. Click at 1, click at 5, click at 5, click at 4, click at 5, click at 3, click at 5, click at 2. Now, suppose we are about to color this graph. How many colors do you need so that no two adjacent vertices have the same color? It is an easy guess, okay? Because these 1, 2, 4, 3 are away. They are not adjacent. Only 5 is adjacent to all. So my guess, let us see, my guess is all the end vertices can have one color, 5 can have a different color. It can be colored with 2 colors. Let us see. You can use any one of this quick color and all same. Let me go for a quick coloring. Yes. Some other noise is here. See, it says that number of colors is 2. Number of colors is 2. 1, 2, 3, 4 are colored with one color. 5 is colored with the second color. Okay. Now let us see here. You see here. Don't you see here? This is 5 is colored with green and 1, 2, 3, 4 are colored with red. So this is about coloring. So what is coloring? Coloring of a graph is coloring the vertices of a graph in such a way that no two adjacent vertices have the same color. Suppose if you shade the states in India with the same color when they are adjacent, they will be mixed, right? So you should give Tamil Nadu a different color, Kerala a different color, Andhra a different color, Karnataka a different color, so that the states are visible. So this is, you can convert the map into a graph. Okay, that is another issue. Okay, let me go for another graph. Let me augment this graph. Let me add this 1 and 2. So obviously 1 and 2 should have different color. Okay, let us see. Let me again go to this graph. Let me go to this quick coloring. So it says number of colors 3. 1, 3, 4, 1 color. Second vertex 1 color. Fifth vertex 1 color. Okay. So let us see. See here, 1 is red, 4 is red, 3 is red, 5 is 1 color, and 2 is black. So you do it with 3 colors. Let me add one more edge over here. Okay. Now let us see. The coloring. Chromatic number is 3. So this, if you go to this menu, it will tell you about the chromatic number. Quick color may give you color which is not minimal. Okay, this tell you about minimal point coloring. The chromatic number is 3. Let us see. It is still colored with Three colors. Three colors. You see the menu. If you don't see colors, so see the menu over here. See, vertex 1, 3 are 1, 3 are colored with one color. 2, 4 are colored with the second color. 5 is colored with the third color. Okay. So you imagine if you have a colored graph, I mean a complete graph. Let us try a complete graph. This is a. I will draw this. 3 vertices, 3 edges. Okay. What about coloring this graph? If 1 has to have a color different from 2 and 3, 3 has to have a color different from 1 and 2, 2 has to have a color different from 1 and 3. Okay. So it should obviously have 3 colors. The complete graph. Let us try this. Click on this. You see that the chromatic number is 3. 1 is colored with one color, 2 is colored with the second color, 3 is colored with the third color. Okay. So this is about coloring of a graph. So you can design a real world problem into a graph. Okay. For example, coloring of India's states, what you can do, you can consider each state as a vertex. And if 2 states are adjacent, join those 2 vertices which represent states. So you will get a graph. Okay. So when you apply coloring to it, you will be able to find the colors with which these states in India can be colored. Okay. So if you want to frame a timetable using this coloring problem, one of my students did that. Okay, the entire exam timetable she framed with using a coloring. That was her MPhil dissertation. How do you frame this exam timetable? Exam timetable, a student may have a paper and a arrear paper also. He should not have them on the same date. That means if you consider the vertices are the classrooms, 2 vertices should be colored differently. Okay, colored differently so that he appears on different dates. Let me go back to the presentation. See, this is what I was telling you about. Let me recall. One thing I missed: the center of the graph consists of vertices whose eccentricity is minimum. Okay, I told you about the coloring. The minimum number of colors required for vertex coloring is called the chromatic number. So you can give a number of, for teachers, you can give a number of exercises to students on coloring. Okay, you know the answer beforehand. You draw any random graph, find out the chromatic number, keep with you, then go to the classroom for the standard conventional exams. You can draw the graph on the board so other students work on the coloring. If there are 60 students in class, you can give them 60 graphs so that each one finds a different chromatic number. They cannot copy from each other. So this is an advantage to teacher as ICT tool. You need not teach graph theory online. Still, you can generate many graphs for you for your class purposes. You need not always restrict yourself to the examples given in the book. Okay. And what about cut vertex? The cut vertex is a vertex. Obviously, if you remove that vertex, the graph will be removed, separated into 2 components. Let us see that. What are the cut vertices in a graph? Let this, I will add one more vertex to it. Okay, let me add some more edges. So this is a graph. You see, if I remove the vertex 3, what will happen? The graph will be split into 2 components. This 1 and 2 will be separate. This will be separate. So 3 is a cut point. And what about a bridge? The bridge, is it here? Bridge. A bridge is a edge. When it is removed, the graph splits into 2 or more components. Okay, a bridge will not be in any cycle. So let us see cut points and bridge, how to illustrate them. I have this graph. I told you 3 and 4, 3, 4 can be a bridge. Okay, when it is removed, let us try it. Let me ask for bridge as a graph. Go to the graph menu. Ask for cut points. What are the cut points? I told you only 3. Let us see what are the other cut points. There are two cut points, 3 and 6. They are colored here. 3 is a cut point, 6 is a cut point. If vertex 3 is removed, okay, let me show it to you how to remove a point. Let me remove this point 3. You see that I am removing this now. See, the graph is split into 2. Okay. How do I do that? Go to this menu, remove a point, delete a point, and delete a point. Click on this and click on 6. See, the graph is split into 2 graphs. So 3 and 6, I am undoing it. 3 and 6 are cut points. They are cut points. So cut point, finding a cut point is a very good exercise in graphs. You can teach the concept and you can give them lot of exercises and innovative exercises. Okay, you can take a real problem where the vertices and the edges can be drawn. For example, you can consider the network of what is that telephone poles, okay, and how they are connected. The telephone poles will be vertices. If two are connected, then it will be an edge. And about network, computer networks in your office or university, if two computers are connected, the computers will be in vertices, and if they are connected, then that is a edge will form over there. So you can find out, if you remove one computer, the entire network can be disconnected. Then that particular computer is a cut point. Okay, if I switch off that computer, get out of the network, then some other computers will be disconnected from it. Okay, so let me see about bridge. What happens if I remove the connection between this 3 and 6? Maybe 3 is a computer, 6 is a computer. I disconnect the connection between 3, and then there will be two disjoint graphs will come. Two components will come. Let us try it. Graph, let me go for bridges. So a bridge is 3, 6. A bridge is 3, 6. It will be highlighted here. See here, a bridge will be 3, 6. Let me remove that bridge. Let us see. Delete an edge. I will click on 3, click on 6. You see that the edge is removed and the graph is split into two components. Okay, two components. This is a not a connected graph. This has got two components. This has got two components. Okay, whereas this is a connected graph, and 3 and 6 is a what is this? An edge. Okay. Let me go to further PPT. Automorphism. Automorphism is automorphism of a graph. It tells the number of ways the same graph can be mapped onto itself. Suppose there are only two vertices and a line. It can be put like this. It can be swapped. Okay, two can come to one's place, one can come to two's place, and it can be mapped onto itself. So it is an automorphism. How many ways a graph can be mapped onto itself without disturbing the edge vertex connectivity? Okay, the graph automorphism problem is a very good problem. The problem of testing whether a graph has a non-trivial automorphism. Let me tell about the Eulerian path. Eulerian, this I will come to this concept. Eulerian path is a path. Yeah, what is a path in a graph? A path in a graph is a walk in the graph. You start with a vertex, go to one more, go to one more, go to one more vertex, and keep moving. This is a path. Okay, and so that every edge is covered exactly once. That's the Eulerian path. If every edge is covered and if you come back to the starting edge, then it's an Eulerian cycle. A Hamiltonian path is a path that visits each vertex exactly once. Eulerian concerns about the edges, and the Hamiltonian concerns about the vertex. Where is the practical applicability of the Eulerian this thing? It may be about a courier fellow, a postman. Okay. Okay, let me get back to the diagram. Let me draw something. Let me open already saved graphs. There is a number of list comes with grin. Let me open. Yeah, already I told you how to draw graphs, so I will be using. So I will have to closing in another 15 minutes. I will be using the already typed in graphs. Let me go to Hamiltonian problem. Okay. Let me go to a net, Hamiltonian net. So this is a graph that is drawn. Okay, you can color the vertices and all that. Now this is a graph. Let me see where is the Hamiltonian path, whether there is a Hamiltonian cycle. Let me check this. Property, graph, Eulerian path. So it will ask me, where do you want to start? Eulerian path doesn't exist. There is no Eulerian path over here. So I told you about, Hamiltonian. Hamiltonian path. It is asking me to select the source point. Let me select the source point. See, it is showing, see, you see that it is running like anything. Okay, it is running like anything. It is showing so many Hamiltonian paths in this graph. You see here, so many Hamiltonian paths. For example, Hamiltonian path is 20, 19, 18, 17, 16, 15, 14, 21. Okay, the weight is 90. There are 19 edges over here. Let me see the red one from this to this, this to this, this to this, this to this. It is covering all. See that? Let me try whether Hamiltonian cycle exists. Select source point. Let me select a source point. See, there are so many Hamiltonian cycles. So many Hamiltonian cycles, which you will not be able to do in the classroom by hand. It will be very difficult. So you can ask them to find the Hamiltonian cycle. Each student can find a different Hamiltonian cycle. Okay. What's a Hamiltonian cycle? You see that, see here, starting from 20, go to 19, go to 18, go to 17, go to 13, go to 12, go to 11, and end with 16. Okay. Let me see this. See here, I started here, moving here, moving here, moving here, moving here, moving here. All vertices I am covering. See that? Exactly once I am coming back to this. Right? So this has a Hamiltonian. So you can draw any graph, see whether it is Hamiltonian or not. Let me draw my own graph if you want. Let me try whether Eulerian. Let me select. I told you about automorphism. I will show you the Peterson. So this is the Peterson graph. You know about this graph, it's a very famous graph. And what about the automorphism? That is, I have this graph, and how do I interchange? How do I paste the same graph on itself? A different vertex on a different vertex, but the edge vertex combination incidence should not be changed. How many ways it can be permuted? Let me see this as a graph. Sort automorphism. Sort automorphism. See, 120 ways. In 120 ways, so this is 10 will be on 1, 7 will be on 2, 6 will be on 3, 8 will be on 4, 9 will be on 5, 5 will be on 6, 2 will be on 7, 1 will be on 8, and so on. You have 120 automorphisms of the Peterson graph. All are listed over here. Okay. So this is about this. Let me see what else I am missing. I told you about minimal spanning tree. Minimal spanning tree problem is another big problem in graph theory. You can give it to students. You can learn with various trees. So you draw a graph. Minimal spanning tree is a tree within that graph. Okay, within that graph with the minimum number of edges, you should connect all the vertices in the graph. Simple. The shortest path problem is going from one vertex to another vertex with the shortest possible distance. The maximum capacity is path problem is to find a path joining two. This applies to weighted graphs. Maximum capacity path problem is to find a path joining two fixed vertices of an edge weighted graph, such that the minimum edge weight is maximized. Let me illustrate this to you. And the k shortest path is the next one. See, the shortest path is one that gives you the actual shortest path. K shortest path is going one step down. It is not only asking about shortest path, but also next K minus 1 shortest path, which may be longer than the original shortest path. This can be found out. And the traveling salesman problem can be found out. I will illustrate all this quickly. Traveling salesman problem is the challenge of finding the shortest yet most efficient route for a person to take a given list of specific destinations. See, a traveling salesman has to visit all the points, all the stores or something, but he needs the shortest path. Okay. Multiple traveling salesman problem is another that can also be attacked here. If I have time, I will show you. Maybe you can have 4 salesmen and 10 cities. Each city must be visited by a salesman while requiring the minimum total cost. This can be addressed. Maximal flow problems involves finding a feasible flow through a single source. You might be, those who know graph theory knows this better. Each edge is labeled with a capacity. What is this problem? Suppose I want to transport cement sacks, cement muttai, from the cement bags from one Chennai to maybe Madurai in any sorts possible. The cost is not a botheration here, but I want to send as many cement bags from Chennai to Madurai in as many ways as possible. I can send through a bullock cart, I can send through a van, I can send through a big lorry, I can send by cycle. So each have a different capacity. A cycle can have at most 2 to 3 cement bags. A lorry can have 100 cement bags. A small van can have about 20 cement bags or something. A cycle rickshaw can handle 5 cement bags, like that. So each you should use the maximum how much pump from Chennai to Madurai. If I want to know this, then I will have to apply this maximal flow problem. Okay, let me get to illustrate the remaining parts and close in 10 minutes. Let me open, I showed you automorphism. Let me show about a graph in chemistry. This is a graph in chemistry. You see this, I don't know the name of this. Some chemistry is allergic to me from day 1 of school. This is a chemical graph. What can be studied with this graph? Anything can be studied. For example, I can find the whether Eulerian path cannot exist over here, obviously. Let me see cut points. What are the cut points? 3, 5, 9, 11, 13. So 3, 5, 9, 11, 13 are the cut points. So this is one example. Let me go for any further example. Petri net, I am not going to illustrate. I will just show you how it can be. I am not getting into this now, because I will have to define Petri net and all that. So Petri net problems can be addressed. So that's what I can say now. Let me, special networks, social networks. Social networks can be studied. For example, office, so there you will see 2 file forms here. It can be saved as a net or NEXT. Net is the comprehensive, which will store the picture and all that. Next can store the names and other information about the graph. Net is comprehensive. Let me open this. So this is a social graph. What's a social graph? Maybe it's a COVID contact. Okay, COVID contact graph. If a person is with how many persons he was in contact. With how many persons he was in contact. You see that this person was in contact with only this person. Whereas this person was in contact with this person, this person, this person, this person. Okay. So this is a social graph. If you want to study the density of this graph, let me see the density of this graph, for example. See, the density is 4. Density is 4. 4, 6, 7, 8 is a click. Okay. Less only because this has so many vertices. The density should be very, very high, but the density is low as far as only this is concerned. So the density of the spread is low as per this contact graph business. Let me go for one more illustration. I have to show you about I forgot about maximal flow problems. This minimal spanning tree. Okay. Let me draw a graph quickly. Let me draw edges. I am connecting as many edges as I can. Connecting 2 and 4, connecting 4 and 3, connecting 2 and 5, connecting 5 and 6, connecting 6 and 4, again connecting 4 and 5. I'm connecting as much as possible. Now let me see the minimal spanning tree. What I told you, minimal spanning tree is a tree. What's a tree? Tree doesn't have cycles. Tree is a graph without cycle. Let me find a small tree, a subset tree in this graph, which connects all the vertices. That's a skeleton. For example, 1 and 2 is connected. Over we see 2 and 4 are connected this way. 2 and 4 are connected via 5 also, via 6 also. So let me have only one connection between 2 and 4. Let me try this. Let me treat this as a network and ask for the minimal spanning tree. See the menu, minimal spanning tree. Minimal spanning tree weight is 5 and the edges are given here. They are colored here. See here. This is not included. The red ones are included. So this is the minimal spanning tree. Okay. Let me see the shortest path. What is the shortest path? It is asking me to find out 2 points. I am putting 1. I am putting 6. What is the shortest path? Source is 1, sink is 6. The shortest path is 1 to 2, 2 to 4, 4 to 6. Okay. Shortest path is 1 to 2, 2 to 4, 4 to 6. If you give weights to these edges, then the shortest path may vary. Okay, you can attach weights to this. I don't have time now. Okay, the shortest path is a path that connects 1 to 6 in shortest possible. The longest path is also there. You can go from 1 to 3, 3 to 2, 2 to 4, 4 to 5, and 5 to 6. That is the lengthiest path. Shortest path is 1 to 2, 2 to 4, and 4 to 6. Where do you need the shortest path? Suppose it is for a fire engine. A fire engine has to start from its place and to a place which is put on fire, set on fire. Okay. Then the fire engine needs to know the shortest path. There are so many streets connected through. If he must know the shortest way to reach that place. Okay. There may be the longest way. So it will help them to find out the shortest way for the fire engine to start and end with the quickest possible route. Let me see what else is remaining there. Salesman problem. The flow problems will come when you have edges over there. I mean weighted edges. Let me try salesman problem and conclude. Salesman problem, I should select the source 1. Okay. From 1, what is the solution? The cycle is 1, 3, 4, 6, 5, 2, 1. It is colored here. See, 1, 3, 1, 2, 5, 6, 4, 3, 1. The salesman starts from 1, goes to 2, goes to 5, goes to 6, goes to 4, and goes to 3, and comes back to 1. This is the traveling salesman problem. Okay. So let me conclude with this. Let me get back to the presentation and show you what are all the things that were shown to you. This is, I repeat, my contact information 6380557735. You can ping on me my WhatsApp. I have over 3000 contacts on WhatsApp. Any information sent to me can be spread quickly to others. Any information about webinars and all that can be quickly transferred by me to over 2000 people instantly. This is what, so this is where you can download this. I will show that website that is outdated. Still, I will show it to you. See, this is the website. It says that this page is outdated. Okay, I don't know what happened to this creator. Some other website in some other Russian language is live. I am not able to read it, but still from this website you can download the software. But how to purchase this software is not very clear to me. Certain other website claims to sell this at $30 for 500 vertices. I have not tried it, but this is enough for us. This version is enough for us. Okay. Let me show what were done. See this as a network. You can find the minimal spanning tree, shortest path that I illustrated to you. The maximum capacity path and multi-salesman problem were not shown. I don't have time now. Okay. As a network, you can find the critical path. Critical path option will be enabled only when you have a project. You have a project. Let me open the project and just show it to you. I have already typed it out. It is already there. This is a project. So this is a project. What's a project? It has a start point, it has a end point, various activities swept. Okay. So it will tell you about the critical path that will be enabled only for this kind of project. So see, the critical path is shown over here. You follow? Okay. This can be taken as a separate class. Okay. So this was covered, and then if you consider as a graph, you can go for the metrics. You can go for quick coloring. Quick coloring, I tell you, it need not give you the quick coloring. Need not give you the minimum coloring. Point coloring will give you the minimum coloring. It will tell you about the chromatic number. You can learn about Eulerian path, Eulerian cycle, Hamiltonian path, Hamiltonian cycle. You can learn about cut points and bridges. You can learn about automorphisms. And the simulation and SNA procedure I didn't touch. Okay. I think I have now. I will close my sharing of this screen. Let me stop sharing my screen. I am coming back to the yes. Feedback link somebody will provide. I don't know. And what I have shown you how to learn and teach graph theory with the help of this graph theory interface software. Graph theory interface software as an ICT tool. I hope I have shown you this. It can be downloaded and it can be used. Now the session is back to Professor Muthuswamy, please.
Thank you, sir. Now I request the participants, if you have any questions, you may ask our resource person.
Professor Venugopal.
Yeah.
I have a doubt.
Yeah. Yes.
I have a doubt. You said you can find the
Echo. I'm not hearing.
Sir, your mic is echoing. Sir, your mic is echoing, sir.
Hello.
I am hearing double echo. Yes.
Yes. Can we find the edge coloring of a graph using this, or should we write any program so that we can find the edge coloring?
No, as of now, I see only vertex coloring there. Maybe available with the extended version. I don't find edge coloring over here in this minute.
Okay.
Only vertex coloring is seen.
Okay. Thank you, sir. Thank you.
Yes. Yes. Yes.
Anybody else has any query?
Hello, I am
Yes.
Shivakumar. Sir,
Yes.
I want to know if we can draw graphs using data from an Excel sheet. Is it possible, or do we only have to draw it here?
The Excel interface is there. And I have not tried it, but the Excel interface is there. What you can do, I told you that's a network, and the property is a matrix is open. No? I showed you how to fill in weights over there. Maybe you can try pasting from your Excel sheet over there. I show you the menu. Let me that the Excel. The compatibility is there. Though I have not tried, it should be possible. Compatibility with the Excel template is there. Okay.
Thank you, sir. Thank you, sir.
I tell you, you download that green software. Along with that green software, you will be getting the example sheets, and the Excel sheet folder is also there. You should be able to import Excel table within that. Should be possible, but limited. You can work only with the 40 vertices, not more than that. Yes.
Thank you, sir.
Anybody else with any query? The participants are asked to fill the feedback form. The feedback link is being posted in the chat box. E-certificates will be sent to their registered mail IDs on completion of the feedback form. I now call upon Dr. B. Shivakumar, Professor, Department of Mathematics, to propose the vote of thanks.
Good morning to one and all. it is my privilege to propose a vote of thanks. At the outset, our heartfelt thanks to the speaker, Professor T. Venugopal, for having readily accepting our invitation and deliver a talk on basic graph theory with GRIN. Thank you, Professor. I hope many faculty and researchers not familiar with the aspects of graph theory and the use of GRIN greatly benefited from the talk, and hope they would take it forward in the research and the uses of GRIN in teaching and research. I place on record our sincere thanks to the management of Rajalakshmi Engineering College, our chairperson, Dr. Mrs. Thangam Meghanathan, and our vice chairman, Dr. Abhay Meghanathan, for their continuous encouragement and support for the conduct of the programs and webinars. It is my duty to thank our principal of Rajalakshmi Engineering College for his visionary leadership and continuous encouragement to the conduct of webinars. I also thank the technical team who supported us in conducting this webinar. On behalf of the HOD, Humanities and Sciences, and the Faculty of Mathematics, I extend a heartfelt thanks to all the participants who made this program a grand success. Thank you, one and all.
Thank you, sir.
Yes.
Sir, welcome, sir.
Cholunga.
Sir, thank you very much for your informative, inspirational, and interesting session. Definitely, the session will help the faculty members to use the software for their teaching, research, and other academic aspects, sir.
Yes.
We will be in touch with you in our future endeavors in REC, sir. Thank you very much, sir.
I have only illustrated the software as a demo. It is up to the participants to explore into this. If they face difficulties, they can get in touch with me. Okay. Thank you.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Thank you. Thank you. So, shall we leave the meeting?
Yes, sir. Thank you, sir.
Sir,
Shivakumar, sir. I'm reaching Shivakumar.
Shivakumar illa sir inga.
As I left the meeting.
ஆமா சார் அப்படிதான் சார் காட்டுது இல்ல உள்ள பார்ட்டிசிபென்ட்டா காட்டல சார்.
Okay, I'll talk to him over phone. Okay, ma'am. Okay.
Thank you, sir.
Anand, sir. Yeah, thank you, madam. Thank you. Thank you.
Sir, good morning, sir.
Sir,
feedback எப்போ சார் க்ளோஸ் பண்ணலாம்?
கொடுங்க சார். 10 to 15 minutes time கொடுங்க சார், because it is